Hello everyone, I am Vedant Naik, currently pursuing Masters in Construction Engineering and Management at SEPT University. As a part of a Studio-2, we have worked in a group of 4. This semester Studio focuses on the construction execution, monitoring and control. For that, we have taken a project of High-Rise Commercial Tower. So now, let us explore the execution part of 41-story structure. Beginning with the project brief and project details, it involves the construction of commercial high-rise building comprising 4 basement and ground plus 41 floors, accommodating a total 309 units of offices of varying size. The building's overall height stands at 154 meters. The contractor's scope of work entails the core and shell construction of the 41-story structure under a labor contract spanning 31 months. Moving on the project highlights, it is a greenfield project occupying a site area of 6,127 square meters with a total built up area of 78,773 square meters. The estimated project cost amounts 500 crore with the land cost of 72 crore as per RERA documents. The project situated in the city of Ahmedabad, Gujarat. The project's location is depicted in the satellite image provided. The project objective is to establish tallest commercial tower in the state of Gujarat, featuring premium showrooms and office spaces. The project benefits from excellent transportation connectivity. The city is linked to international airport located 18 kilometers away from the site, while the railway station is just 11 kilometers away. Additionally, the city is well served by metro lines for internal transportation, with the nearest metro station situated just 2.2 kilometers from site. Now, let's dive into the site layout planning, a crucial aspect at the onset of any construction project. Beginning with the existing site layout, certain planning assumptions were made, like offices were designated along the 60-meter highway for convenient access, while materials taking space were allocated along the 18-meter wide road to facilitate easy material unloading and avoiding traffic disruption on highway. All the offices are positioned along the 60-meter wide highway, while steel yard and materials taking space are situated along the 18-meter wide road. Each component is identified with numbering in the existing site layout, with the legends provided in an accompanying table. The site features 3 entrances. Gate A serves as the main entrance for contractor and client staff. Gate B is utilized for material loading, unloading and direct concreting using concrete pumps. And Gate C is designated for labor entry and transit mixer access for column concreting using concrete buckets. In the 3D layout of existing site, two cranes of 60-meter and 30-meter radius are depicted, with the tower area representing the typical floor area to be constructed up to the 41st floor. Further comparing the existing site layout with guidance from National Building Code, CPWD and Safety Health and Environmental Regulations, several critiques and suggestions were made. The water near curing tank risks damaging material stored in the materials taking space. To address this, it is proposed to switch the materials taking space with the client office. Further, lack of dedicated parking spaces necessitates proposing a parking area near a toilet facilities, as indicated in the proposed site layout. Absence of a dedicated scrapyard result in the scattered scrap placement. Hence, a scrapyard is proposed at one corner of the site, replacing the tea stall, which is subsequently relocated adjacent to the scrapyard. The security cabin distance from the gate compromise the security. Thus, it's suggested to relocate the security cabin near the gate C for enhancing surveillance. Moving forward, we have identified a total of 38 risks for the site, with 10 of them specifically linked to the site layout. A risk register has been prepared and a risk matrix has been developed to illustrate the probability and impact of each risk. For instance, SR01 concerns the risk associated with the transit mixture entry-exit via gate C. Due to the absence of dedicated pathway for workers, the probability of accident during transit mixture movement is high, potentially leading to the significant project impact. Similarly, under-equipped quality control lab not in compliance with CPWD guidelines poses a high impact on project quality, so probability and impact of that risk is also high. Additionally, the site establishment cost has been computed. This cost is determined by dimension of all components and includes material, labor, and equipment cost. For example, offices like the project manager's office, contractor and client office are container based, so their costs are determined through market rate analysis. Also, in steel cutting and bending yard, equipments like cutting, bending, and threading machines are used, so in that, equipment costs were also considered. Considering all the factors, the total site establishment cost amounts to 3 crore 17 lakh 55,061 rupees, inclusive of the labor colony establishment cost, which is situated 900 meters away from the site. Lastly, the proposed site layout, reflecting changes based on the previously identified critics, has been presented. The orange mark indicates the modification made. Firstly, internal switching of number 8, which is client's office, and number 4, which is the material staking space. Further, the proposed scrap yard at number 15 and the proposed parking space at number 16 is presented. Moving into pour planning involves organizing and scheduling activities necessary for concrete pouring in construction buildings. Continuing with the pour planning activity, we have focused on formwork, reinforcement, and concrete planning. In a formwork planning, certain assumptions were made, like slab cycle for basement 4 to basement 2 is actual. The typical floor cycle is assumed of 20 days till the 7th floor and 14 days afterwards, based on inventory and labor availability. And for planning purposes, we have considered only 3 typical pours in the tower area, marked in the layout, which is pour 1, 2 and 3. This pores covers the area of 597, 369 and 710 square meter respectively. On site, Peri-alpha deck formwork is used for slab. For column, Peri-handset alpha is used, and for beam, Peri-alpha deck ply and Peri-up MI staging system is used. To calculate coefficient for formwork element of horizontal members, we observed the actual area containing all formwork system components and quantified each components. Grids were prepared for the observation and shown in the first figure of grid. For instance, the slab components grid details the quantity of 2.4 meter by 1.2 meter panels, verticals and drop head in the observed slab area of 43.2 meter. The coefficient for each component was calculated using the formula quantity calculated for a particular element divided by area of the grid taken. For example, if there were 25 vertical observed in a grid area of 43 meter, the coefficient would approximately 0.58, thus rounded to the 0.6 and shown in the coefficient calculation table. Using this coefficient, the quantity of each element for each pore was calculated by multiplying the area of slab for each pore by deducting the beam area from the total pore area. Similarly, grids were prepared for beam detailing the number of primary and secondary VT girders and for components of Peri-up MI staging system, which is shown in the last two grids. Ply for vertical and horizontal face of beam was also considered. For the vertical face, the full depth of the beam on the outer face and the deduction of slab depth from the beam depth on the inner side were factored in for ply calculation. Based on these grids, coefficient for cross-headed splinters, ledgers, ledger brace, top standards, base standard, VT girder, ply and shikanja were calculated. Continuing with the vertical member calculation of column elements, which is done differently from the horizontal members, as we have different size column and for each two different size handset alpha panel were used. So for that, in pour 1, 2 and 3 there are total 32 number of columns were identified and which is categorized in 6 different categories based on their size, and calculation for all categories is done separately. The plan illustrates the typical setup for column category of size 1200 by 900. In this setup, handset alpha panel of size 1.5 by 0.9 meter and 1.5 by 0.6 meter are utilized. These panels are horizontally tied with a tie rod and vertically with wedge clip and corner connectors, which is stacked one above another. Unit quantities for all components like handset alpha panel, base plates, alignment system, tie rod, spacer tube, wing nut counterplate, and scaffolding bracket were determined through on-site observation, and total quantities were calculated by multiplying them with the total number of columns in each category. Moving to the set code repetition for slab formwork, actual repetition dates are considered until the second basement, with subsequent cycle predicted based on planning assumptions. On site, there is one full set of panels and two set of scaffoldings are considered. The repetition for ply is considered 8 times and change in ply are reflected in the set code repetition. Lastly, going to the direct cost of formwork, calculation are based on the quantity of all components. Unit price of each component are multiplied and repetition for each elements are factored in to determine the per repetition cost. In this direct cost table, A illustrates the cost of ply and panels, B represents the cost of scaffolding and staging system, C denotes the labor cost calculated based on the labor requirement per pour per day and their daily wages, and D and E represents the TEP and water and electricity cost, which is calculated based on 1% of A plus B plus C. Moving further with the cost of quality, it falls under quality management, which ensure all work conforms to specified quality standards. The cost of quality encompass expenses related to the maintaining quality standards and rectifying poor work quality, comprising both the cost of conformance and non-conformance. The cost of conformance is divided into two parts, prevention cost and appraisal cost. In prevention cost, we have considered four different expenses. The cost of preparing quality assurance plan and checklist entails accounting for the salary of those involved in their preparation, based on their time taken. Equipment cost in the quality control lab are determined by equipment's lifespan and project duration. The cost of establishing the QC lab includes materials and labor expenses. Additionally, for labor training cost, we considered the salary of the persons involved based on time allocated for the training. Regarding appraisal cost, all expenses are calculated for the entire project duration of 31 months. This includes the cost of maintaining and calibrating equipment based on the calibration schedule. The cost of controlling incoming materials accounting for salary of a store personnel involved. In-process quality control cost includes the salary of a QC personnel involved during the construction. Routine test cost calculated as per the test for cement and steel. And external audit cost is calculated considering the salary of a senior engineering personnel from the client side based on approximate total number of hours utilized. The cost of non-conformance is divided into two parts. Internal failure, where the cost of rework due to non-conformance is considered, and external failure, which is calculated post-project handover and therefore not included in this calculation. Based on this, the total prevention cost amount to 3,57,497 rupees, in which 60% of the total cost attributes to the equipment cost. The total appraisal cost stand at 1 crore 20 lakh 47,404 rupees, with 80% allocated to the cost of controlling in-process quality and 16% to the cost of routine test. Continuing with the cost of non-conformance, we have considered two non-conformance activities from the site. NC1 is strengthening of the slab due to excess cracks. There are total 29 cracks are developed in the slab portion of the pore 4 and 8 cracks were developed on the skin wall. Due to this, leakage, seepage and moisture entry problems have been occurred in the COP area slab. This image shows the cracks which are developed on the slab area, and the causes for the NCR inadequate structural design, as two longer span supports are not provided despite being a one-way slab, resting only on 200 mm thick skin wall on one side. The other cause of NC is due to improper curing shrinkage in concrete is developed, and ice cool concrete is not used as per the structural guidelines. As per this, for NC1, the cost is calculated based on the following factors. In material cost, the expenses for grouting materials and glass tape are accounted. Equipment cost includes the rental of the grouting pump and the cost of injection nozzles. Manpower cost includes the salary of engineers and labor based on their times and hourly wages. The total cost of NC1 considering this factor is amount to 17,843 rupees, in which material cost comprising the highest portion at 34% of the total cost. Lastly, the summary of the cost of quality encompasses the cost of conformance and non-conformance, including prevention and appraisal cost as well as the cost of internal failure. The total sum is 65,96,419 rupees. Appraisal cost makes the highest portion of the cost of quality, which is accounting for 96% of the total cost. As a part of our studio, we are also focused on the concept of lean construction. For that, we have undertaken two key deliverables, one of which is a value stream mapping. To gain a deeper understanding of value stream mapping, let us begin by examining the five core principles of lean. Starting with the value, value is defined as what the client is willing to pay for. Value stream involves the mapping of client value within the current process flow and identifying any wasteful elements. Flow is defined by eliminating waste. We aim to establish a continuous flow of work, thereby increasing the time allocated to value adding activities. And based on that, establishing a pool based system application to lean tools like JIT. Based on that, at the end, pursue perfection and strive for continuous improvement. Now let us apply this principle to the specific activity observed, which is the concreting of COP area slab. The observation period span from 10 am to 8:46 pm, encompassing lunch and tea breaks. During this time, 56 cubic meter of concrete were poured. The observed flow of activity begins with the cleaning of the casting area, followed by connecting of concrete pipes, mobilization of tools and equipments, concreting by TM1 through TM8, and concludes with the post-concreting activities. To analyze current state, we categorize observed time into value-adding and non-value-adding activities based on the duration of each sub-activities. Cycle time for each activity was determined by subtracting start time from finish time, accounting for parallel activities. In the current state, value adding activity consists 36%, while the waste accounts for 64%, comprising both non-value adding and non-value adding but necessary activities. Waste within sub-activity was identified using the downtime lean concept, categorized into two types of muda. Type 1, which is non-value adding but necessary, and type 2, which is non-value adding activity, that is shown in the table of waste categorization. Following the analysis, the takt time for the current state was calculated by determining the ratio of time taken to complete the concreting, resulting in 10.5 minutes per cubic meter for current state map. Conversely, the targeted takt time was calculated based on the labor productivity assumption and set at a 6.5 minutes per cubic meter, which is shown in the graph of takt time. To achieve the targeted takt time, various lean tools such as just-in-time, 5S, Kaizen, and Pokyok were applied to identify wastes, aiming to reduce the non-value adding time in the process. Several examples of these applications are provided in the initial table. Type 2 waste, which represent non-value adding activities, was entirely eliminated. The example for that is activity 1.6.1. Meanwhile, type 1 waste, which denotes non-value adding but necessary activity, time of that activity is reduced to certain extent. Example for that is 1.6.4 activity. As a result of applying lean tools to mitigate observed waste, the future state mapping was conducted. This resulted in achieving a takt time of 6.3 minutes per cubic meter, which is closely aligning with the targeted takt time of 6.5 minutes per cubic meter, which is shown by a graph of takt time. A comparison between the current and future state illustrates a significant reduction in the cycle time by 234 minutes. Consequently, the activity can now be completed in 354 minutes in the future state, approximately in 6 hours, compared to the current state duration of 9.5 hours, which is shown in the graph of current state versus future state. Coming to the conclusions, all the deliverables were done as a part of the entire course duration, out of which the key learnings taken from the ones discussed in the portfolios are site layout planning. In our site layout planning, we have scrutinized our current layout against CPWD, NBC and SHE guidelines, learning about essential elements for standard layouts. We then crafted a new layout incorporating these guidelines driven adjustments. Further going with the pore planning, in which we have learned to calculate formwork material requirement per pore by developing coefficient for different elements. Additionally, we have mastered predicting slab to slab cycle based on the labor productivity and availability of sets, and understanding repetition cost and developing re-requirement cycles. Further, in our exploration of quality management, we have delved into the cost of quality, recognizing it as a compressing cost of good quality and cost of bad quality. We have calculated the cost of over the project duration of 31 months. Lastly, in the lean construction through VSM, we have scrutinized slab casting, successfully reducing type 1 waste and eliminating type 2 waste, resulting in an overall time reduction. At the end, we learned that recognizing activity like concreting, which is daily occurrence on site, minimizing delays in this activity is crucial to project timeline and adherence. Thank you.